Yeah, let me see what I can do. Okay, so in Newtonian gravity, it doesn't matter if the object is spinning or not. The gravity is going to be the same, right? We could be in orbit around the sun if it wasn't spinning just the same as we are now. But in Einstein's gravity and general relativity, it actually does matter if the object is spinning, because as it moves relative to space-time, with that spinning motion, it actually kind of interacts with the space-time and causes this kind of back reaction almost. And so that can affect other objects nearby. So for example, an object might have more mass if it's traveling spinward and less if it's traveling anti-spinward, or maybe it's the other way around, I forget. Anyway, and like most things in general relativity, there's a ton of math associated with this, and it only applies in kind of strange regimes, so things like black holes, and it's actually been measured for some satellites in orbit around Earth, so pretty cool. Okay, disclaimer, I am not a particle physicist, but I'm going to do my best here. So all particles are either fermions or bosons based on their spin. Now note, this spin is not a physical spin, it's just like the intrinsic angular momentum of the particle, so we call it spin. So why is this an important categorization? Well, only fermions have antiparticles. So an electron and a positron, for example. Bosons don't have antiparticles. There's no such thing as an antiboson. However, bosons can be each other's antiparticles or their own antiparticles, in fact. So that's kind of weird. Also, and this is very crucial, only fermions are bound by the Pauli exclusion principle, which means that no two fermions can have the exact same quantum state. Bosons totally can. Hello, Bose-Einstein condensate. Okay, so then what the heck is a hadron? So a hadron is any subatomic particle that is made up of quarks. Hadrons can be fermions or bosons, depending on how many quarks they're made up of. So if they are made up of 3 quarks, then they're going to have half integer spin, they're going to be fermions. And if they're made up of a quark and an antiquark, they're going to have integer spin and they're going to be bosons. So the fermion hadrons are called baryons, and the boson hadrons are called mesons. Confused yet? Also, composite particles can be bosons, but they are not hadrons because they're not subatomic particles. So for example, the helium nucleus is a boson, not a hadron. Yeah. Absolutely. So I actually just did a video on YouTube about parallax, so if you want a lot more info, you can check that out. But let's do parsecs real quick. So the Earth goes around the sun once a year. Hopefully we can all agree on that. If you're not on board for heliocentrism, you're probably on the wrong channel. Now, if at 2 different points in the Earth's orbit, we observe a nearby star, the location of that star relative to further away background stars is going to appear to change by some small angle. We'll call that P. P for parallax. Now if P equals 1 arcsecond, which is a unit of angle, then by definition the distance to that star is 1 parsec. And this is just from geometry, knowing that we are 2 AU away when we're on opposite sides of our orbit, and then there's a right triangle. So a parsec is just a unit that was defined because it's easy, because we use parallax to measure distances to nearby stars. Oh, and it's about 3¼ light years. Light travels incredibly quickly. The speed of light we know today is about 3 × 10⁸ meters per second. So in order to measure this, you need either very accurate and precise timing equipment or a very long distance to measure. And that is actually how the very first measurement for the speed of light was made by the Danish astronomer Ole Rømer. So basically, if you have an event that you know when it's happening, and then you measure the difference in when you know it's happening versus when you observe it's happening, this can give you a speed of light. And this is what he did by realizing that the difference in the observed transits of Jupiter's Galilean moons was actually due to the finite speed of light. And so therefore, he calculated it took an extra 22 minutes for the light to reach us based on our location in Earth's orbit. So this gives you a speed of 11 minutes per AU for the speed of light. Now that's kind of a strange unit, but it is a speed. And if we translate that into meters per second, it's actually 2.2 × 10⁸ meters per second. Not bad considering this was back in 1676. This is actually a really fun one. So it used to be the case that they did not know if the speed of light was finite or if the speed of light was instantaneous, if it could just be infinitely anywhere. And actually the very first measurement was made by a Danish astronomer called Ole Rømer based on the difference in times between the transits of the Jupiter moons based on what they expected versus what they observed as the Earth was on different sides of the solar system. And basically he used this to say this is an approximate speed of light. Now he was a little off. But he got like really close for being the first ever person to measure the speed of light and prove basically that the speed of light was finite. And then of course there have been much better experiments, including one of my alma mater graduates, Michelson, who actually received a Nobel Prize for his work in measuring the speed of light, and also his work with Michelson-Morley on the measurement of whether or not there was a luminiferous ether. So yeah, we've done a lot of work on measuring the speed of light. Oh no, you're not going to be swimming through liquid water at the center of a planet, and here's why. So this horizontal line in the middle here is 1 atmosphere, and so that's what we typically think of for water. So this is a phase diagram of water, right? So when it gets cold, on the left side you're going to have ice, in the middle where it's like kind of warm, it's going to be a liquid, which is the green, and then if it gets hot, you're going to get vapor, it's going to evaporate, and that's on the right. But at the center of a planet, you're not at that pressure. Oh no, you're way up here. So the pressure at the center of the Earth is like 350 gigapascals or so, so you're like way up here. And basically water has to be solid at that pressure. There's just too much pressure pushing it together for it to be anything other than a solid. This is called high pressure ice, and so the ice that would be at the center of the planet would be this ice 10 or ice 11, which is, woo! That was a wasp. Which is basically just referring to how the crystalline structure of the ice is arranged, but yeah, no liquid water.
Alright class, let's take advantage of this beautiful fresh blackboard to talk about more refined measurements of the speed of light.
So this is the setup that Michelson used that's called a Fizeau-Foucalt device. So you have a lens in between 2 mirrors set up like this, and you also need a source of light. There you go. So now the light is going to travel from the source, bounce off the mirror, go to the lens, and be focused onto the second mirror, where it's a mirror, so it's going to reflect back to the direction and go back to whence it came. Now, if you make this mirror a rotating mirror, the same thing is going to happen to begin with. So the light is going to leave the source, bounce off the mirror, go to the lens, go to the other mirror, go back the other direction. But now this first mirror will have moved by some angle, and so it won't reflect back to the original source. It will actually be offset by 2 theta. So if you know the distance between the 2 mirrors, call it h, and the speed at which the mirror rotates, which we'll call omega, you can solve for the speed of light using this equation. And there you go. Ta-da! Win yourself a Nobel Prize. This is an interesting question. So what you're basically asking here is, what is the speed of gravity? So the reason it takes 8 minutes for light to reach us is because of the speed of light and the distance between the Earth and the Sun. So how long it takes gravity to reach us is going to depend on the speed of gravity. Now in Newtonian gravity, gravity was actually considered a kind of instantaneous field. That is, the speed of gravity was infinite. But general relativity predicts that the speed of gravity is the same as the speed of light, in which case the answer to your question would be yes. So have we actually been able to confirm this? Yes, and this is super exciting because we've only been able to do it with this really amazing multi-messenger detection of both gravitational waves and light from the same event, and by the fact that they arrived here at the same time, we were able to prove that, as Einstein predicted, the speed of gravity is the speed of light, so that's pretty exciting.